Hi everyone, welcome to lecture number 10. In this lecture, I'm going to teach you the specific regression model called logistic regression. So this is the regression model for a binary outcome. So that is to see the outcome which is yes or no, or disease, non-disease, mortality, alive, such like that, right? And here's the outline. So I'm first going to introduce the model specifically using the mathematical equations. So this including two models, simple logistic regression and also multiple logistic regression model. So if you remember, we talked about simple linear regression. So that's the linear regression with only one predictor variable, or one independent variable. And the multiple regression model will include more than one. That means two or more independent variable as the predictors. So it's similar here. Simple linear regression, the simple logistic regression will be a logistic regression with only one independent variable as the exposure. But multiple linear regression is the regression model for a binary outcome, but include multiple independent variables. And then I will briefly talk about the estimation of the loss ratio using the logistic regression model. Basically, I will give you a quick review. Hopefully you guys will learn from your EPI class is the 2x2 table to get the loss ratio and see how the logistic regression model can obtain the odds ratio similar to when you get the 2x2 tables. And then I will use an example to show you how to test effect modification. And that is also called interaction in a multiple linear regression. And this, I don't post the real data for this example. So this is just a demonstration. And this example actually uses data instead of SAS. But at the end, I will give you a SAS example. And also I post the data set on the web, which is the SAS data set and also the SAS code to use the dung fever example and see how we can use the logistic regression model to estimate the parameters and also do hypothesis tests in logistic regression. And at the end, I will give one specific topic, and this is how we can use receiver operating characteristic curve, or we call ROC curve, to evaluate the predictive accuracy using after we run a logistic regression model. So basically, the logistic regression model will give you the predictive risk for a certain event. So if the event is a disease, and then you have a risk for the disease, and then we can use the ROC curve to evaluate the accuracy of the prediction based on the logistic regression model. All right. Okay. So first of all, I'm going to briefly introduce the goal of the logistic regressions. So the main goal to do here is to examine the exposure effect on the outcome. An outcome should be binary, and also we can adjust for potential confounders. So it's going to be a multiple logistic regression because we can include more than one predictor variable. So that means you can have one main exposure, and also you have multiple covariates. Here is the figure. So you actually saw this figure in lecture number 3. We talked about the confounding thing in multiple linear regression. But similar here, the only difference from this model to the linear regression model is here the binary outcome outcome, the outcome have a binary, it's a binary data instead of a continuous data. But the figure is the same when we try to evaluate the confounding effect. And here, the confounding variable, what we call confounders, can be continuous variable or can be categorical variable. That means a variable more than 2 categories. And also it can be an ordinal variable. All right, so just a quick review. So in order to identify a confounder, the confounder has to be statistically correlated with the exposure and also correlated with the outcome. And the main goal here is to evaluate the effect of the exposure on the outcome. But in order to be a confounder, the confounder has to be correlated with both exposure and outcome, but not in the causal pathway. That's to say, it's not the intermediate variable from exposure to the outcome. All right, but at the first example, so I will still go over this. Okay, so here is the model setup for logistic regression models. So logistic regression analysis is the most popular regression technique available for modeling the dichotomized, or we call the binary independent variable. It can be used to describe the relationship of several independent variables from x1 to x2 to xk. So this has to be in multiple logistic regression model. And then we can see the association between these independent variables to the dichotomous or binary dependent variable y. And here y is the typical coded, it's typically coded as a 0 and 1, as I said, for its 2 possible categories. So for example, it can be 1 can be disease and 0 can be non-disease, or 1 can be mortality, 0 can be alive. And also you can code this not only as disease, but can be other kind of events. The events can be beneficial events instead of a harmful event. The logistic regression model specifically describe the probability of your event outcome equal to 1, so which is the expected value for binary variable in terms of this form. So here we model the logit form of the probability. P is denoted the probability of y equal to 1, and the y here is your outcome variable. So for example, if y is your disease variable, or disease say is hypertension, so the p will be the probability that the cohort have probability of hypertension equal to 1, or in other words, this is the proportion or the percent, or in epidemiology we call the risk of hypertension in your study cohort. So the way we model that is we'll model the logit of that probability. So the logit is defined as the log of the function of the probability. And here, the function is p divided by 1 minus p. And if you still remember this from your epi class, p minus p over 1 minus p is defined as odds in epidemiology. So here p is the probability. P over 1 minus p is to see what's the chance of an event versus not an event. So this is defined as the odds. So the log of the odds will be modeled as a linear combination of the predictor variable. So here we assume we have a total number of k independent variable, or k predictor variable in the model. So the generic form for the logistic regression model is the log of odds ratio, log of odds, or log of the probability over 1 minus probability of a certain event defined by y is a linear combination of the predictor variable or independent variable. And this model link the disease. So if we call y equal to d, so if y indicates certain kind of disease, and then this will link the disease probability with an exposure and confounders. So for example, if we use x1 as the exposure, and then x1 is the e, and all the other x from x2 to xk will be the confounders if your scientific question is to evaluate the effect of your x1 or exposure on the outcome y. And here with the dichotomized outcome y, p is the expected value of y, or we call it expectation of y. So in a cohort study, so that means if you enroll a study cohort and follow them up, this probability is equal to the expectation of y. In other words, that's the probability of y equal to 1. The reason the expectation of y is equal to the probability of y equal to 1 is y only have two options, 0 and 1, and therefore the probability or the expectation of y is just the probability of y equal to 1. So this is simple mathematics. And this is also equal to the probability, the event y within a specific time period. So in terms of the epidemiology terms, this is a disease prevalence. In a case control study, so which is a study you do retrospectively, and you can collect a number of cases, and then you also collect a number of controls which mask the cases. So that's the case control study. Again, you probably learned that from your epi class as well, or a study design class. In the case control study, the p here, the probability is also equal to the expectation of y, or the probability of y equal to 1. But here, the specific p here is defined as the probability of a case. And then p divided by 1 minus p is the odds, or the odds of the case. In the cross-sectional study, the cross-sectional study is the study at a certain time point, which is like a snapshot of the time period without any follow-up. This probability p, again, is expectation of you event y equal to the probability of y equal to 1. And this p is the probability of disease present. Because we do not have a follow-up, we cannot define this as prevalence. It simply just tell you at a specific time point what's the probability the disease present in your study population. Okay, I'll just give you a very simple math through the logistic regression model, because this is important, and a lot of people sometimes may not get this very clear, even though it's not a very complicated mathematics. Here we can use beta 0 to beta k to represent estimated value of beta 0 to beta k. So beta 0, beta k is probably just the true coefficients, but your b0 to bk is the estimated coefficients after you run the logistic regression model. And then you can easily calculate the probability of the event. So for example, this is the probability of the disease, or this disease prevalence in a cohort study. So this is simply equal to a ratio of the exponential function of all the linear combinations of the predictor variables. In the numerator, this is exponential of the linear combination, including the intercept terms and also each terms of the predictor variables. The denominator is 1 minus that function. And here you can see the denominator is always greater than the numerator. And this will guarantee that the probability is less than 1. So which makes sense because probability or percent of disease is always less than 100%. And this will guarantee, using a logistic regression model, you can guarantee that you predicted probability or the risk of a certain event is less than 1 and also greater than 0. The reason is exponential function is always greater than 0. And therefore, both of your denominator and the numerator will have a value greater than 0. And therefore, the ratio is always greater than 0, but less than 1, which is guaranteed by the denominator is greater than the numerator. And this is a way you can calculate the event probability after you have the estimate of all the regression parameters from your logistic regression model. So this is a simple math. The reason is if you put both left-hand side and right-hand side with exponential function, so the log will goes away, and the right-hand side will be the exponential of all this linear combination. That means P over 1 minus P is equal to E to that, the whole thing, the whole linear combination. And you can just do a simple math to factor out the P, and the P is equal to the form like this. And here again, as I said, this will always guarantee the probability or the risk of certain disease is always greater than 0%, but less than 1 or 100%. And a lot of people can also use the linear regression model to predict the binary outcomes, because if you have a large number of sample size, a large sample size or large number of study participants, somebody can still assume that the expectation of your Y is approximately normally distributed, and then they use the linear regression. But one big advantage of using the linear regression to predict the probability is it cannot guarantee the estimated probability is less than 100%. And in a lot of situations, you might have an estimated probability of disease greater than 100%, which is not possible. Or sometimes you may have the estimated probability less than 0%, which is also not possible. But it will be possible if you will not use the logistic regression, but you use linear regression. It is possible you can have out of normal range probability estimation. All right, and here I just give you a simple relationship between the probability or the expectation of your binary outcome Y and the predictor variable X. So here I only assume there's only one predictor variable X. And then the logistic regression model will give this we call S shape. So this is to say, if your X is equal to 0, the estimated probability is around 0.5 or something like that. But it's not necessary to be 0.5. It really depends on the study setting or your data set. But the shape is like S shape. As the your X increase, it's kind of flat at the beginning, but the increase of your probability exponentially in the middle. But at the end, I mean when your probability is close to the cap, the ceiling, 100%, is also get flattened, and also is flattened at the other limit, which is the floor value of 0. Okay. So here, I still have like some other comments about the model itself. So here, logistic regression model considered as a generalized linear model. So I'm not going to give a detailed introduction of the generalized linear model. Generalized linear model really means this is a linear model in the form, but just not linear model itself, but is after certain transformation of the expectation of your outcome y, and you have a linear terms. So you can easily see that linear part. So basically on the left-hand side of your model, this is a function of your expectation of your outcome y, because P here is the expectation of outcome y. So this is, we call a logit function of expectation of your outcome y is equal to a linear combination. So this is the reason we call this generalized linear, because we have these linear components. But these linear components is not directly modeled based on the expectation of y, but this is a function of the expectation of y. We call the logit function of expectation of y. And this is defined as a generalized linear model. It's not the real linear. Generalized linear means the transformation of the expectation of your y can be written as linear forms. And this is a linear combination of all the predictor variables, and also include the intercept term beta 0, and then beta 1, x1, all the way to beta k, sk through the link function. And the link function is the logit function. So in such a way that the logit function of the expectation of your y is equal to the log of P over 1 minus P. Again, P here is still the probability y equal to 1, or the expectation of y. And here you may know if the P probability or the risk of disease is the function, and then this, if P is the disease probability, and then P1 over 1 minus P is the odds of the disease. So this is why the logistic regression can be easily interpreted in terms of a epidemiology concept, which is the odds ratio. Okay, and here's a quick review how we can link, or how we can relate logistic regression model with a simple 2x2 tables. And you might see this 2x2 table a lot, especially in the epidemiology class. So here's the setting. So if you want to do this 2x2 table, so you will have a exposure variable we call E, not E. So the column is defined by the status exposure. E means this is the status exposed to a certain risk. Not E means not exposed. And then the row is defined as the disease status. D means you have the disease, and not D means it's disease free. So basically, in each cell defined by these 2x2 tables, basically 2x2 table, we have 4 cells. 2 times 2 is equal to 4. And each cell, you will have the number A, B, C, and D indicate the frequency for each specific combination. So for example, A is the count, or the number of diseased subjects exposed to the risk. And B is the number of disease but not exposed. Similarly, C is non-diseased subjects exposed, and D is the non-diseased subjects not exposed. And the odds ratio is easily, you can see, is defined by A over C over B over D. So you can see A over C is the probability or the frequency of disease divided by the frequency of non-disease, specifically under the exposure group, right? So A rho C is similar to, is the same as A over A plus C over C plus A plus C. So A over A plus C. So A plus C is the margin total, is the column total, is the number of subjects exposed to the risk. So A over C is the probability of disease among those exposed to the risk. And C over A over C is the probability of non-disease subjects among the exposure group. So basically, A over A plus C over B over C over A plus C is just the ratio, and that is the odds, right? Because that's the probability of disease over probability of non-disease. But if you do that simple math, the A plus C part will be canceled out because both numerator and denominator will have A over C, have over A plus C, and that part can goes away. And therefore, A divided by C, or A over C, is just the odds of disease among the exposure group. So similarly, B over D is the odds of the case among the N exposure group. And therefore, A over C over B over D is the odds of case in the exposed group over odds of case in the N exposed group. And this is defined as the odds ratio. So the odds ratio is the odds of case or odds of disease between the exposure group and the non-exposure group. And if you do a simple math, this A over C over B over D can be simplified as A times D over B times C. And you can see A times D is basically just the diagonal, the product of the diagonal of the 2x2 table if you do a configuration like this. And B times C is the product of the off diagonal in this 2x2 table. Okay, and this is how, but later on I will show you how we can match this odds ratio calculated from the 2x2 table with the parameter beta from the simple logistic regression model. Okay, and the property of the logistic regression model is the predictive values of probability P or risk of disease P are always between 0 and 1, and this is guaranteed by these logic functions. I already talked about that. And the model is geared to the odds ratio, and it's another good benefit, and it's another benefit, a good part of the property of the logistic model, because it simply matches the odds ratio, which make the interpretation much easier, the interpretation of the beta parameter much easier. And also the drawing effects of the two variables are multiplicative. So the multiplicative means, so say here, simple linear regression model, we have two effects. One is the, it's not really two effects, but two parameters. So one is the intercept, the other one is the slope parameter, or this is the parameter of the effect of your exposure x1 on your outcome y. And here you can see in the simple logistic regression model, we can estimate the probability of P equal to the exponential of this plus over 1 plus exponential of this. So the reason we call multiplicative is if you address the or express the exponential of a summation. So this is equal to the exponential of beta 0 times the exponential of beta 1 x1, or that's the product of exponential to the beta 0 and exponential to beta 1 times x1. And therefore, between the two variables, so if you have more variables, and all these joint effects will be multiplicative instead of additive. In the linear regression models, no matter that's a single linear regression or multiple linear regression, the effect we call this additive, because it's not on the exponential scale, it's on original scale, and therefore is additive. But on the exponential scale, the exponential of summation is equal to the product of exponential to each terms, and therefore they are multiplicative instead of additive. All right, and then I'll specifically talk about simple linear regression. So that is the, simple logistic regression. So that's the logistic regression model with only one predictor variable. And here I will give the specific interpretation of these parameters, beta 0 and beta 1. And again, for quick review, the model is given by the logit of P or log of the odds of P. We model that with intercept term beta 0 plus the effect of your exposure. So that is given by beta 1 times x1. And here is the interpretation of your beta 1. So here I divide into two different situations. So the first situation is your x1 is a continuous variable, and the other part is x1 is a binary. But it's also possible x1 is categorical variable, so that means more than 2 categories, 3 or more categories. But you can do that similarly to the interpretation as if x1 is binary. If x1 is continuous variable, and then the beta 1, which is the estimated value of beta 1, B1, is the log of odds ratio for 1 unit difference in the predictor variable x1. In cohort and cross-sectional studies, the exponential of beta 1 is the odds ratio comparing two populations with 1 unit difference in the exposure defined by x1, defined by the exposure x1. So you can easily see that if we give exponential on both hand sides, so this part is the odds for a certain population with a x1 value as a reference value. But if you add 1 unit of your x1, and you actually have another odds, and the ratio of that two parts is the interpretation of your beta 1. So your beta 1 just give you for 1 unit difference, right? Because if you add the value of x1, you put them as a difference, and then you minus 2 part, and then this beta 1 left over is actually a ratio of your odds, and therefore we call this odds ratio. And if your x1 is binary, and then the estimated parameter of your beta 1, which is B1, is the log of odds ratio comparing exposed versus unexposed group, assuming the unexposed group is the reference group. In cohort or cross-sectional studies, it's exponential of the estimated coefficient B1 is the odds ratio between exposed and unexposed group. So because here, if you have a binary predictor variable or binary exposure, you only have 2 possibles. So one group is the exposed group, the other group is the unexposed group. And therefore, you can only have 1 comparison. And that comparison is the odds ratio between exposed group and unexposed group. So this will be very, very similar. to these 2x2 tables. And the beta 1 parameter, if you get exponential of that beta 1 parameter, it's exactly equal to the odds ratio. You calculate it using the 2x2 table. All right, and then next one is the beta 0. So remember, beta 1 is the key part because beta 1 will specifically give you the relationship between exposure x1 and the outcome y. But the beta 0 is sometimes because it's nuisance parameter. It's not a parameter of interest, but sometimes people are still interested in interpreting the beta 0 coefficient. And here, if beta 0 is a continuous variable, the exponential of the estimated beta 0 or exponential B0 is the odds of being diseased d equal to 1 at x1 equal to 0. So you can simply see that. So if you put x1 equal to 0, and this part will go away, the only leftover is your beta 0. The estimated is B0. And at the time, B0 without x1 effect is just the odds. So the exponential of that, because if you go both part exponential and this logarithm goes away, and the exponential beta 0 is just, we call it baseline odds. So that's the odds of disease at x1 equal to 0. If x1 is a binary and you actually code x1 as a 0 and 1, and if x1 equal to 0 indicate the n exposed group, and then the exponential B0 is the odds of being diseased or d equal to 1 for the n exposed group. Because if you add that part, that's the disease group, but without that part, the beta 0 itself will be the log of odds for that non-exposed group. All right, so this is interpretation of the parameters in a simple linear regression. That is the simple logistic regression. That's the logistic regression with only one exposure. Or one independent variable, or one predictor variable. And in a multiple linear regression, this interpretation becomes a little bit more complicated. And again, the model is still in a similar form. We model the log of the odds using a linear combination with effect from x1 to xk. So if your scientific question is still to see the exposure effect on the outcome, and you put exposure as your x1 and x2 to sk as your covariates or confounding variables, you will have a model like this. And then your interest in the interpretation of your beta 1 or B1, because this is the part this is your main scientific question, right? The main scientific question can be answered by beta 1 or B1, because that's the effect you are being evaluated, or that's the effects of exposure on the outcome. Again, I divide this into two different situations. So if your x1 is continuous variable, and the estimated beta B1 is the log of odds ratio for 1 unit difference in x1, that's exposure, one or other covariates or factor from x2 to sk are held constant. So here you have to say that because you adjust for the variables from x2 to sk. So after adjusted for these variables, the beta 1 or B1 is interpreted as the log of odds ratio, or in other words, as the adjusted log of odds ratio, or the exponential of your B1 will be the adjusted odds ratio. And if x1 is a binary variable, that's to say x1 is exposure versus non-exposure. And then the B1 is the log of odds ratio comparing the exposed versus unexposed groups. And assuming the unexposed group is a reference group, when all other covariates or factor from x2 to sk are held constant. So this is similarly way how the other covariates from x2 to sk constant, and this beta 1 or b1 is the estimated that we call adjusted log of odds ratio. The exponential of b1 is the adjusted odds ratio when you held all the other adjusted variables constant. For the beta 0 bar, similarly, if x1 is continuous, and then the exponential of beta 0 or b0 is the odds of being disease when the exposure variable equal to 0 because the exposure is continuous. When other covariates are all equal to 0 and other factors at the reference level. Okay, so other covariate equal to 0 means if among the variable from x2 to sk, if some of them are continuous, we need to have the continuous variable at 0. Or if some of these variables are categorical variables, we need to have this categorical variable equal at the reference level, because at the reference level is coded at this variable equal to 0. So it's basically just the odds at all these other predictor variable, including exposure and other covariates at level 0. And if x1 is a binary, the exponential of beta b0 is the odds of being disease for the n-exposed group when other covariates equal to 0 and other factors at a reference level. All right, so here the interpretation will be a little bit complicated because you have more than one independent variables in your model. So that's interpretation for multiple logistic regression model. All right, I will just quickly go over the estimation. So this is statistical intensive, so which is not a goal, basically not a goal in this class, but I just want to quickly go over. So in case you are interested in the detail, you can go from here. So basically how to estimate the regression coefficient from beta 0 to beta 1 to beta k. So the method we use is called the maximum likelihood estimation. So the maximum likelihood estimation, I already talked about that in linear regression, is we need a likelihood function. So likelihood function is based on the distribution. So we need to know the distribution function in order to specifically write up the likelihood function. And therefore we can use statistical method to maximize this likelihood. And the beta will be the coefficient, the estimated coefficient will be the coefficient that maximizes the specific likelihood function. So likelihood function is just the probability of observing the data given the parameters. So remember the parameters here are beta 0 to beta k. So for example, we have 3 predictor variables from x1 to x3, and then we have 4 unknown parameters, including beta 0, beta 1, beta 2, and beta 3. And then the likelihood function, the distribution function is very easy because you see your outcome is binary. And basically, the data is we call the binomial distribution. So binomial distribution, you only can choose from 2 different kinds, or 2 different categories, or 2 different choices. And the likely function of the binary likelihood is just the probability times the number of the frequency or number of cases with probability pi. So remember the pi is the diseased or the event. So the yi will be the number of events or number of disease cases. And 1 minus yi will be just the non-disease cases. So for certain situation, like just for individual case, so this yi can be either a 0 or 1, right? So 0 means this is a control. 1 means this is a case. So if this is a case, you will have power 1 to the p. And 1 minus p will have a power 1 minus 1. So remember, 1 minus 1 is 0. So everything to the power 0 is 1. And that means this power goes away. So when you're adding all the subjects, or from 1 to your sample size, you actually have a product of what the summation of these cases. So this is have all the number product of number of events times pi in times, and this pi is a mathematical notation of the product. So this means you have the product for all the number of events, the event subjects with probability pi, and then times the product of non-event subjects with, because all of them have the probability of 1 minus pi, because the pi is the estimated probability of the disease. So every single subject will have probability p of disease and probability 1 minus p of disease free. Okay, and then if you plug in all this estimate to p, you will have a likely function like this. Because the logistic regression model, if you go back to the model, so the model will give you the relationship between p and all these parameters. And then if you just plug in that parameters, in this case with 3 predictor variables, you will have a product like that. And the way to do that is in terms of each parameter being estimated, you can actually do a partial derivative. So if you still remember, I show so how we can do the partial derivative in lecture number 2 when I talk about the least square estimate. So here the likelihood function is a similar likelihood function. We want to have the estimate which maximize the likelihood, but in the least square, we want to get specific beta that minimize the square error. That's the squared from the observed value to the estimated value. But here is a little bit different function. Your base function is different. You're not using the error function. You are using the likelihood function, but the mathematical method is similar. We'll all get the derivatives in terms of this parameter. And then for each parameter, we can have an estimate because the estimate is just the solution of the derivative equal to 0. Because when the derivative equal to 0, will either have a minimum value or maximum value. But this we can guarantee. This is the likelihood function is a function we only have the maximum value. There's no minimum value for that. Okay, so that's the detail for how you can estimate a beta parameter. So this is too statistical intensive. So that's definitely the range of the study, but I just want to give you some of this background. But it's optional for you to understand or to know the detail. But if you don't know detail, that's okay. So the other part I want to just give you the idea, because in practice studies, sometimes there's a lot of situation. You can see the phenomenon we call over dispersion. And the method to solve this issue is we can use a beta binomial model. So what is over dispersion? So over dispersion is a phenomenon that occurs frequently in the application of binomial data. So remember here in the logistic regression model, we're dealing with the binomial data, yes or no data, 0 and 1 data with disease, non-disease data. And this describes a situation in which the variance of the data, which is variance of the outcome y given the pi, the probability, exceed the binomial variance, so which is equal to the sample size n times p times 1 minus p. So theoretically, so if you have taken the introduction to statistics or the distribution or probability class, you may still remember if you have a binary data follow the binomial distribution, the variance of the binomial distribution is p times 1 minus p. And then because you have the product of n subjects, and the total is n times p times 1 minus p. But in reality, because you assume your data is binomial, but sometimes it may not be a perfect binomial distribution, and it's very likely the true variance in your data, or variance calculated from your data, is greater than or much greater than the theoretical variance np times 1 minus p. And often this over-dispersion occurs due to clustering in the population from which the individual are drawn. So if you do a sampling design, so if you assume the perfect sampling design is you have a totally random sampling, and you can have all the typical samples from the population. But if you sampling just like clustering around, you will have a lot of subjects with a similar characteristic, because you're like, say, you draw them from, like, say, same families, for example, they will share the same genetics. And if you draw some of them from the same geographical location, and they will share the same location and same environmental factors there. And therefore, you may not have a perfect random sample, but instead you will have a cluster sampling. And this will give you a sample size, which will give you a variance, which may not have the correct variance based on the binomial distribution. And these clusters may correspond, like I say, families, geographic areas, or genetic subgroups. And then the integration over random effects of the clusters will lead to the beta binomial Marshall model. So we're not going to introduce specifically the beta binomial model, but here I just want to keep in mind, if you have this over dispersion problem in your logistic regression, you may think about using the beta binomial Marshall model instead of the logistic model. And also the quasi likelihood inference assume the variance of data is inflated by a factor alpha, and the maximum likelihood can be used in the situation when you have over dispersion. And also the other options is you can use the Bayesian inference instead of the regular inference, because the regular inference, as we talk about on this page, is based on binomial distribution, because you see the likelihood is entirely dependent on the data follow a binomial distribution, and therefore you can write this likelihood as p to the y times 1 minus p to the 1 minus y. All right, so here's some statistical issues or statistical considerations, but it's very technical. But here I just want to give you this information in case in the future you might meet this situation. You see this we call over dispersion, or the inflation of the variance when you compare with the theoretical variance. You might think about that, but you mean if you do not know that, you can still consult a statistician, but you need to keep in mind this might be an issue, and this happens very frequently in real data examples. All right. Okay, and so I want to talk a little bit about hypothesis testing for the association in logistic regression model. So primarily, so if we want to test the association between exposure and the outcome, the null hypothesis is there's no association between exposure and the outcome. And the alternative hypothesis is there is an association between exposure and the outcome. And then specific in the setting of logistic regression, the null and alternative hypothesis can be represented by using the association measure, odds ratio, or if you still remember the estimated parameter beta 1, we call the B1, that is the log of the odds ratio. But if you give exponential function on that B1 parameter, and what you will get is the odds ratio, and then you can have a 95% confidence interval for the odds ratio. You can also have the p-values for the odds ratio. You can base on either the 95% confidence interval or the p-values for the odds ratio or for log of the odds ratio beta parameter to do the hypothesis testing. In terms of the odds ratio, the null hypothesis is odds ratio equal to 1. The alternative hypothesis is not odds ratio not equal to 1. So remember, the odds ratio equal to 1 means your beta 1 equal to 0, right? Because exponential of 0 is equal to 1. So the odds ratio equal to, we compare odds ratio with 1 instead of 0 is because if the odds ratio equal to 1, that means the odds in the exposure group and the odds in the exposure group is the same, right? Because we're not looking at a difference, we're looking at the ratio. So only if the ratio equal to 1 means the equivalence of odds between the exposure group and non-exposure group. Okay, all right. In next one, I want to give a little bit review on how we can identify confounding variables or confounders in multiple logistic regression. So this would be similar to the way we can identify them in multiple linear regression. The difference is here we have a binary outcome instead of a continuous outcome. So if you still can remember the rule of thumb is if the association measures change greater than 10%, and then we will say there is evidence there is a confounding effect. And here the difference is in linear regression model, the effect is given by the difference in mean. But here, the association measure is odds ratio, and therefore we'll look at the change of odds ratio with a relatively large amount instead of the change in the expected value of your y. Okay, and again, we still use the rule of thumb 10% rule. If the change is greater than 10%, but remember this change will be the change in odds ratio instead of the difference. And then again, through this specific figure, we can say with and without adjust for the confounding, if this effect change more than 10%, or this effect given by the odds ratio change by more than 10%, we can say the specific variable being evaluated is a confounder for the relationship between exposure and the outcome. All right, and the other part is the effect modification, or we call interaction in statistics. The effect modification or interaction can occur when the association between exposure and the outcome variable change or varies over the subgroups in the population. And this subgroups is defined by the potential effect modifier or the variable being evaluated as an effect modifier. And the factor that defines the subgroup is called effect modifier. Okay, so here I want to give one specific example of evaluating the effect modification. And here I don't post the data set here because this is a hypothetical example using the simulated data. It's not a real data set. So I only show the SAS example using the true data. So here is, you can think about as hypothetical example, but the way is to evaluate if there is an effect modification in the multiple logistic regression. And here I use, as I said, I use a data as the software, but you don't have to worry about the software. But the things is like to keep on how we can do the interpretation and how we can do the hypothesis test on the interaction term. So this is the in cohort study that evaluate the association between hypertension at baseline and stroke events within 3 years of follow-up. So as I said, the cohort study is a study you can enroll a sample of study participants, but you follow them up for a certain period of time. And in this specific study, we assume that there's a 3-year follow-up after you enroll the study participants. In the study outcome, we call the Y01, which is the event of interest, stroke within 3 years. So if this is equal to 0, that means you have at least one stroke within the 3 years after enrollment. Equal to 0 means you didn't have any stroke-related event at all within the 3 years. So that's stroke-free for the 3 years after the enrollment. And then we have 3 predictors. H is the hypertension at baseline. So this is a binary predictor variable, 0 and 1. And then we have gender, which is female gender. So 0 is male, 1 is female. And again, this is also a binary predictor variable. And then we also have another predictor variable we call CV1, so which is the cardiovascular assay result, which is continuous variable. So basically we have 2 binary or 2 categorical predictor variable, the 1 continuous variable. And here we want to see if the association is the same in all subgroups, and then there is no interaction or effect modification. So if the association is not the same, and then there's going to be an interaction. And just quick review for testing the interaction, the null hypothesis is that if the odds ratio for males is equal to the odds ratio for females, that means there's no interaction for gender on the main exposure hypertension. But this is not true. That's the H1, which is alternative hypothesis. Basically means the odds ratio for males is not the same as the odds ratio for females. So it's basically we will have 2 odds ratios. So one odds ratio is the odds ratio between hypertension and non-hypertension among male, and the other one is the odds ratio between hypertension and non-hypertension among female. And if the null hypothesis is rejected, so which means we'll reject, which means there is a significant association or significant interaction between gender and hypertension. In other words, the female gender is an effect modifier for the relationship between hypertension and stroke events. And here's the stata output. So this is basically the stata command. So I'm not going to introduce data, but the things is I can just quickly tell you. So we run a logistic regression model using Y01, which is the stroke event as the outcome. And everything after the first one will be the predictor variables or independent variables. So F double hashtag with H will include the main effect by hypertension, main effects by female gender, as well as the interaction between hypertension and female gender. So that's the way we use the hashtag, we use the double hashtag. And here we also adjust for another covariance we call CV1, which is the cardiovascular assay from your blood draw. Instead, I give you this logistic regression model and tell you use Y01 as the outcome. And before that, you have this is the test for the overall model, and this is a p-value for the whole model. So that is the test for the 4-degree of freedom model. That means your model include the main effects from hypertension, main effects of female gender, and also 1 degree of freedom interaction, and the other 1 degree of freedom for the continuous covariance, and therefore you have 4 degree of freedom. And reject the null hypothesis, that's P equal, this is not exactly 0, but the data is not like SAS. SAS will say less than 0.0001. But here, data give you 0.000 really means less than 0.0001. There's impossible you can have a p-value exactly equal to 0. You can have a very, very tiny number, but it's never, ever equal to 0. And then this is say like the whole model is significantly better than the null model. The null model will be the model without any predictor variables, only the beta 0 part. And here we want to interpret is the coefficients for female gender, the coefficient for the hypertension, and also the key thing is the interaction. So the interaction is negative 2.04 with this 95% confidence interval and the p-value 0.02, which is less than 0.05. And here is the standard output for data. And if you're interested in the meaning for each part, this is definitely different from the SAS output. But if you're interested in each part, the coefficient is actually your beta. It's not the odds ratio. It's your beta or log of the odds ratio. And this part is the standard error. And this is a z-test score, and this is a p-value, and this is 95% confidence interval for the beta value. Okay, so as I said, it's basically included two type of tests. One test is the test of the model as a whole, and the other part is the test of the specific variable in the model. So in linear regression, the entire model test, we see if this model is statistically better or significantly better than a null model is through an F-test. But in logistic regression model, that's a likelihood ratio test or score test, but basically it's a chi-squared test. And you can see here it called LR, which is likelihood ratio chi-square test with 4 degree of freedom. In linear regression, if we test the specific variable, like say it can be a main effects, or it can be a 1 degree of freedom comparison between certain level with the reference level for categorical variable, or it can be for continuous variable that's a 1 degree of freedom test for 1 unit change in the value of the continuous variables. That's all 1 degree of freedom test. So that is similar to or same as type 3 F test. So this is the t-test or partial F test. And this partial F test is type 3 partial F test. So they are used for testing each parameter or each degree of freedom defined by the predictor variable. But here in logistic regression model, This test is called a word test. It's not a t-test, but this word test is similar to a z-test. The z-test means we have a normal distribution, we have a perfect normal distribution. It's not t-distribution because t-distribution is approximately same as normal distribution, but it's never equal to a normal distribution. But the word test is actually approximation to the z-test or the normal test, or we can use the restricted likelihood. But here in the Stata, they use a z-test because you have a z-score, or this is a word test. So I will show you this in the next example, what we can see from SAS output, because the next example is the SAS example. All right, and here we want to do the interpretation of the main effects, and also we want to do this for evaluation of the interaction terms. So again, I pose that output. So the main effects of hypertension is given by this coefficient 2.39 with 95% confidence interval from 1.09 to 3.68 with a p-value less than 0.001. And again, 0.000 really means less than 0.001 because they have 3 digits left here with a 0. It's equivalent to less than 0.001 with 3 digits as well. And then here we can easily calculate the odds ratio because the odds ratio is the exponential of the coefficients. The coefficient is the log of the odds ratio. So exponential of that is just odds ratio. So why don't we just do a simple calculation? This is equal to 10.91. In 95% confidence interval for odds ratio, again, you need to do the exponential for the lower limit and upper limit of the 95 interval. So this is equivalent to exponential of 1.09 to the exponential of 3.68. So this translates to the value 2.97 to 39.64, which is a huge value. And also we have a very large effect for with the point estimate equal to 10.91. This is a huge odds ratio. So for gender, okay, so here's the interpretation before we go into gender. So we want to do the interpretation for that specific value, B1. And this is for those who had hypertension at baseline, the odds of having at least one stroke within 3 years is 10.91, 95% confidence interval from 2.97 to 39.64. So you have this 10.91 times the odds for subjects without a hypertension at baseline when the covariate CV1 is held constant in the model. So that's the interpretation for the effect of hypertension. So that's the main exposure. So for gender, so we have this B2 or BF equal to 2.99 with 95% confidence interval from 1.52 to 4.47 with p-value less than 0.001 again. And we can translate this into the odds ratio equal to 19.88 because that's exponential of this 2.99. And 95% CI of the odds ratio is from 4.56 to 87.35. And the interpretation for that gender effect is the odds of having at least one stroke within 3 years for female is 19.88 times, 95% interval from 4.56 to 87.35 times the odds for man when CV1 is held constant. So actually also need the status of hypertension to be held as constant. And then the effect of CV1 is the odds ratio for 1 unit difference in CV1 is exponential of that coefficient 0.196. So that's equal to 1.21. The interpretation is the baseline odds for men without, because man is a reference group for the gender, and no hypertension is the reference group or baseline group for hypertension status. And therefore, we have to interpret this as the baseline odds for men without hypertension, and the 1 CV1 equal to 0 is the exponential of this this coefficient for beta 0, which is a constant terms. So this part in SAS is called intercept, but in Stata, specific called underscore cons is the constant terms is the beta 0. So the interpretation for beta 0, that means you need to let the CV1 equal to 0, let the female gender at baseline, which is male, and add the hypertension at baseline, which is no hypertension. And for that specific subjects, which is man without hypertension and with CV1 equal to 0, is exponential of negative 11.86. This is a very small number. It's equal to 7 times 10 to the negative 6. It's basically 0.000007. So this is, again, a hypothetical value because you do not have any subjects with a CV1 equal to 0, which is not possible in practice. But this is interpretation for that constant terms. It's for that kind of people. A man without hypertension, CV1 equal to 0, will have a tiny little change equal to 7.06 times 10 to the negative 6, have this odds. So this is we call the baseline odds. All right, and the key part here is we want to test the interaction terms. So in order to see if female gender is an effect modifier for the relationship between hypertension and the stroke events within 3 years. And this term can be clearly seen from, we call this B3, a beta 3 parameter. And obviously this is significant because the p-value equal to 0.02, which is less than 0.05. The exponential of that part is exponential of negative 2.04 is equal to 0.13. And also we can translate the 95% confidence interval to 0.02 to 0.72. But you may ask, what does this mean? So here is the interpretation of that. So we can say the ratio of two odds. So that's the stroke odds ratio, the stroke odds ratio comparing hypertension and non-hypertension subjects for women versus the same odds ratio comparing hypertension and non-hypertension for men is 0.13 with 95% interval from 0.02 to 0.72 when CV1 is held constant. So that's the interpretation for these interaction terms. So because you see in the model that we have interaction terms and we have the covariance terms. We need to have this covariance constant. But the interpretation of that interaction terms is complicated. It's actually the ratio of two odds ratios. So remember, the interaction in linear regression is you see the difference of the difference. You have two groups of expected difference in means, and the interaction is basically just the difference in expected values. But here, everything is in exponential scale. So naturally, this interaction terms will be interpreted as the ratio of the two odds ratios. So here is the ratio of the two odds ratio comparing hypertension and non-hypertension for stroke among women versus that odds ratio among men.
and this is equal to 0.13. And because p-value is less than 0.05, so we conclude that the interaction term is statistically significant. In another word, female gender is a statistically significant effect modifier for the relationship between hypertension and the outcome event, which is the stroke, within 3 years. All right, so that's all for the example for looking or evaluating the effect modification and also the interpretation for the main effects. In the next part, I will go over that specific SAS example using a new data set and give you the specific interpretation of the result from SAS output.